Hello, everybody. Welcome to today's current seminar. I'm Nazani, and I'm thrilled to be your host today. Today, we have two speakers, two talks. Our first speaker is Jonathan Lippert. He will be giving a talk on transfer learning-based physics-informed neural networks for magnetostatic static field simulation with domain variations. Jonathan Lippert is a master's student in computational engineering at TU Darmstadt. He was employed as a research assistant at the Institute for Accelerator Science and Electromagnetic Fields at TU Darmstadt. There, he worked on transfer learning for physics-informed neural networks with domain variations in the field of magnetostatic. Currently, he pursued his master's degree and focuses on machine learning and robotics. So with that short introduction, the floor is yours and you can start your presentation.
Thank you for the kind introduction. As you said, my name is Jonathan Lippert, and today we talk about the work transfer learning-based physical informed neural networks for magnetostatic field simulation with domain variations. So the name is programmed today, so we will talk about physical informed neural networks. I assume most of you will know them. And then we'll look at specifically transfer learning for domain variations, and the application is the domain from the electrical engineering is magnetostatic field simulation. So my talk will be structured as the following. I will first start with a quick introduction, and then I will talk about why transfer learning is relevant for this case, and then I'll explain our method and with our workflow there, which we then applied to first a simple example of the well-known Poisson's equation, and then on a more advanced example at a quadrupole magnet. And at the end, we will sum everything up. So let's dive right into it, and we start with the physics-informed neural networks. So those are neural networks that rely on physical information, for example, in the form of a partial differential equation. For example, here a Poisson's equation. And we then can solve this equation by defining a loss function. So here, for example, we can define it by the residuum. We just minimize the residuum. And then if we sample over our certain domain in which the PDE is defined, we can get a solution by training the neural network with this loss function. However, here, one drawback here is that we use the second derivative of our function, which is quite computational costly. And therefore, we can improve this by using the variational form of Poisson's equation. It can be shown that minimizing this energy functional here is equivalent to solving the Poisson's equation we saw before. And we can also incorporate soft constraint boundary values here by simply integrating over the squared sum error between our Dirichlet boundary and the value of our actual function here. And then we punish this error with a punishment parameter beta. And so at the end, the boundary values will be learned. However, it's to say it's only soft constraints, so the function will not have exact boundary values here. This method is known in the literature also as variational pins, since they use the variational form, or also as energy methods, since it's an energy function we minimize here. But to my knowledge, the first one who published it were E and U 2018 with the deep Ritz method. And our paper is based on exactly this paper, deep Ritz. So now we've got a loss function. Let's look at our problem. We are in the electrical engineering domain. So here we have Maxwell's equation, and we want to look at the magnetostatics. That means we can neglect all time-dependent terms here. and only look at the magnetic field and magnetic flux, then we have these three equations. And if we then use the vector potential approach, that the magnetic flux is equal to the curl of our vector potential, then this leads us to a curl equation, which simplifies in 2D to, again, Poisson's equation. So here, again, we have a domain. We can sample over this domain. We have our Poisson's equation here for the magnetostatic field case. We have an excitation current over the domain. We have a certain permeability here for simplicity set to 1. And we have our energy functional to solve this problem. And then we can derive from this variational form our loss. It's simply using Monte Carlo integration here and adding the boundary values by soft constraining them with the punishment weight here beta. And beta is here set to 500. We have the samples inside the domain. The batch has the size of 1000, and the samples on the boundary is set to 100. And eta here represents the learning rate.
Jonathan,
Yeah?
what's the motivation of using the variational form for this problem?
Because we only need the first derivative, so it's computational easier.
But actually, it converges. There's a theoretical work that shows, I actually teach that in my class, that it shows that with a standard pin, the collocation form is like effectively you minimize in the H2, the solution, as opposed to this, which we minimize to H1. So if you use, so the convergence rate, the theoretical convergence rate, at least on the approximation side, is worse in variational form than the strong form.
Okay. Well, I have to admit that's new to me. So
I can show you when you finish. I can show you this slide I show in my class.
I can only say that our motivation was just that it's computational easy, since we only have to calculate the first derivative, and
right. That's a good point. But if you do the JAX, if you do the implementation in JAX, the second derivative is no problem. You're right. If it's TensorFlow Python.
We implemented it in TensorFlow, and there it was quite slow.
Yes, you're right about that.
Yeah. Okay, then
I'll show you a paper after you finish, or I can email you that a paper that shows the theoretical analysis of this. Yeah.
Okay, nice.
Also, one question here: you're computing the L2 norm for the gradient of A using Monte Carlo too, or in your loss, you have L2, right?
Yeah.
Here using Monte Carlo too, or how are you approximating that part?
It's just a Euclidean norm, so no Monte Carlo needed here. But the integral is then calculated with Monte Carlo.
Oh, okay.
Okay. Yeah. Okay, then if no questions are there anymore, I would go on. So we have our loss, and then we need a neural network, so to say an architecture. Here we applied zero input padding, so we just enlarged our input space. Instead of two dimension x and y, we added some more with zeros, so that we have to get more parameters. But from my perspective today, I would change this and would go to maybe a position encoding, similar to the one used in the transformer paper with sine and cosine, that you would have a finer position encoding here. But we use the zero podding. And as an architecture, we adapted the one from the deep RITs. There they used multiple blocks, whereas each block consists of fully connected layers and one skip connections. And we here used 6 of those blocks with the activation function and tangent hyperbolicus, and the input padding dimension was set to 10, which then resulted in a total of 1,331 parameters. And let's talk about transfer learning. Transfer learning is simply trying to take the knowledge which was gained from one task, learning one task, and applying it to another task in order to learn this task better or faster. For example, if you have a data set like ImageNet, there you try to classify whether it's a cat, dog, or whatever. And at the end, you have a good performing model. Then you can go to a different data set, for example, a smaller one with your own data, which is a little bit similar but different. Then you can just use the pre-trained weights from your other task to initialize your new neural network, which normally relates to faster and better results at the end. This is well applied in computer vision and natural language processing and so on. So it might also be interesting for physical informed neural networks. So why is this especially here the case? Because if you look at the state of the art, like finite element methods, they have some disadvantages. For example, meshing is quite expensive. We have the curse of dimensionality for parametric problems, and you have to recompute the whole solution even if you change only small details inside the domain. And pins can overcome these problems since they need no meshing, they're differentiable, they can have multiple input variables without blowing up the parameter space. Like you could parameterize the material parameter, you could parameterize geometry, and yeah. And transfer learning could also speed up and reuse old solutions in order to get faster results. However, pins are quite computational costly, so in order to make them competitive, transfer learning is really needed. So let's look at what we did. We first choose an initial geometry and solve this geometry with the finite element method, and then used this reference solution to train a neural network by the means of mean squared error. And then we had our reference neural network solution from which we started. Next, we choose a geometry variation. Here, for example, a circle, which is quite similar to a square. And then initialized our new neural network with the pre-trained weights, and then trained on the new domain only by the means of the minimizing the energy functional here. And afterwards, we evaluated our results. Okay, let's apply this to Poisson's equation.
Jonathan,
Here,
can I ask questions
yeah.
here? Obviously, you have some constraints with respect to the domain, right? For example, you train on a square, the circle has to be about the same size.
Yeah, that's correct.
Do you have a precise requirement, or is it because the transfer learning will strongly depend on what you of that domain?
So let's take an example here. The square has the size goes from -1 to 1, and the circle has a radius of 1.
Right.
Does this clarify your
question?
Yeah. Okay, yeah.
But I mean, you can take a square and have a hole inside, right?
Yeah.
Just like masking. So that's an easier. Okay. Because if the circle is twice as big as the square, then you're doomed.
It wouldn't make sense. Yeah.
Yeah, exactly.
It would be hard to transfer the knowledge.
Okay. So there's implicit. There is a constraint. You don't have explicit constraint, but there is implicit constraint.
Yeah. It's by our what we choose. Yeah, that has some implicit constraints in it.
A common sense constraint.
Yeah.
Okay.
Should be similar. Like similar is not defined, but common sense. Yeah. Okay. So here again we can see here we have those 3 domains: the square, the circle, the slice. We just defined our size, and the slice also has the same size as the square, but only a different boundary condition here. The Dirichlet boundary condition goes into the domain. That's the difference here. And then we solve those with a finite element method in Phoenix with the open source library here. Okay. Then we also evaluated at the end our results by the means of the relative L2 norm. Here we used not the same finite element solution, but one that has a finer mesh, so that we could be sure that our results were good evaluated or well evaluated. And those were our results. The blue line represents the case without any transfer learning to compare it to. And the green and the orange case were the transfer learning cases coming from the other two domains. And here on the left-hand side, we can see that on the square domain, transfer learning significantly could improve the learning process. And also on the right side, for the circle domain, we could see improvement, which is exactly what we would have expected. However, if we look at the slice domain, here the learning process was slowed down and was not as good as before. So this is quite surprising. And this is also here shown by the errors, the final errors. For the circle and the square domain, it's quite low. However, on the slice, it's way too high. Okay, let's look at a more quadruple magnet. A quadruple magnet.
Jonathan, why is it surprising? Since the slice, you're going to have singularity, right, at the tip, so the solution changes. So that's the problem with the slice. It's not just the shape; it's that the solution has a singularity.
Yeah, that's could be the reason why it's the case. However, why is it then faster to go from one to the other and not the other way around? Like here's well, and here it's not like well, you could say it's due to the singularity.
Oh, I see. But TL from square, TL from circle is about the same, right?
Yeah.
So in either case, you don't have singularity. It's a smooth solution. So that's why. Because we had this problem when we had a domain with a hole, and we tried to go to a domain with the same size hole but square. We introduce the corners, and you have a Laplacian. That's an elliptic singularity. So you don't have that in your solution. So you have to develop it from the transfer learning. That's why that's a problem.
Yeah. So I mean, you could what you learn here, that it's easier to start from nonlinearities, but the other way around is harder because you have to create it out of nowhere.
Right.
Maybe that's what you can take here with you. Yeah. Okay. Then for the quadrupole magnet, it's a quadrupole magnet is basically four magnets laid out in a way that they're opposite to each other. Like here in practice, it's normally an iron choke with copper coils and can be found in particle accelerators where they apply to focus a particle beam. And here we only simulated 1/8 of the magnet, since for reason of geometry, we can derive the rest of this solution from this solution. So here on the left-hand side, again, we have our slice. The green area represents the iron choke, the purple area, the vacuum inside the beam pipe, and the yellow area is the copper coil with the excitation current. And the blue line and the red line represents the boundary conditions. Here we have homogeneous Dirichlet boundary conditions at blue, and red is homogeneous Neumann boundary conditions. And on the right-hand side, again, our finite element solution. And then we varied our geometry in a way that maybe an engineer would do it. We made the vacuum pipe a little bit smaller and a little bit bigger. And those are our resulting domains, from which we then again applied our workflow and to use transfer learning. And here again, we have the finite element solution of those three cases. The the difficulty here was that we had to parameterize first our quadrupole magnet. We did this by NURBS, non-uniform rational B-splines. Here we used 4 for the 3 different materials. However, the one iron was too big, so we used 2 here. Yeah, and sampling from a NURBS is not straightforward, since you basically sample at a unit square. However, then map your samples to your domain. So we had to apply here a small trick. We can say here the equality is given from both distributions, must be equal to 1. So we can rearrange the terms that we can say that the probability distribution of our patch is equal to the probability distribution from where we sample. So the unit square times the absolute value to the power of -1 of the determinant of the Jacobian from this mapping. And then we have our probability distribution. And just that you are not confused, if you look at the paper, in the paper, the unit square is denoted here with the F, U, and U for unit, and the D for domain, and the K represents the patch number, since we have 4 of them. Yeah, and also a quick reminder of Monte Carlo equation. We have the expectation with integrating over the probability distribution and the value function, and we can approximate this by taking the law of large numbers, by drawing a few samples from this distribution and approximate with the sum. And in this way, that's the idea of Monte Carlo integration. We here just insert our new probability distribution, and then we have our function from which we can approximate the integral. And here's again our problem. We have the quadrupole solution and the Poisson's equation. Basically, since our material parameter is has the same value on each patch, so on each patch we have basically a Poisson's equation, and then we can again use our variational form here with our soft constraint boundary conditions to approximate to get our loss. It's maybe worth to denote that the Neumann boundary condition is not explicitly punished, because it's implicitly fulfilled, since we are using the weak formulation here. And yeah, here is the loss. We can see again our probability distribution we derived beforehand, and we punished the boundaries, and we have again our hyperparameters. So let's look at the results. Again, transfer learning from the to the nominal case brought the expected results. It was faster, it was better. However, if we look at the other 2 cases, we can see that the transfer learning on variant 1 on the left-hand side first started with a smaller error, however, then started to grow first, and then converts slower than the case without transfer learning. And on the right-hand side, we have also a quite interesting behavior. Here it converges quite fast until one point where it starts to grow again, and then stops at a higher error than the case without any transfer learning. And this is also the case for the final errors. So for the nominal case, it's quite good. However, for the other 2 cases, way too high. So let's sum it up. What we've found is that transfer learning can be really beneficial for physical informed neural networks. However, it's not always the case, so you have to really pay attention which case applies here. And the next step would be to examine under which circumstances it's beneficial or not. We just discussed it beforehand. Maybe it's the nonlinearities and other points that's maybe work to do here. And I want to add one more thing, because during my experience, I found that there's a really high sensitivity to the hyperparameters, especially better together with the batch sizes for the domain. and the boundary, and it led to a funny behavior here. First, the convergence was really good, but at one point, it started to grow again and diverges, and this was due to bad hyperparameters. So maybe that's also one thing that could be further examined. And here, as I said, the work was basically based at a Deep Ritz paper, and it's the paper is published. You can find it at Wiley's in the International Journal of Numerical Modeling. And now, if you have further questions, I'm happy to answer them.
Thank you, Jonathan, for your great talk. Now we open the floor for questions. Do we have any questions from the audience for the speaker? And yes, George put the paper in the chat. Yeah.
I had a small question. This is Varun from Brown. Jonathan, how many layers you use for the transfer learning to train?
So it's the architecture I explained. It has 6 blocks. Each block has 2 layers, so 12 layers. Plus one final layer, I think, so it should be 13 layers.
So do you train the last layer only, or did you train more than one layer?
No, I trained all layers. I trained all weights.
For transfer learning part as well?
Yes.
Why did you do that, Jonathan?
Good question. I didn't specifically choose it to do that like that, because you could have also added new weights and only adjust them. We came to the conclusion that maybe it would make sense to retrain all, because then not everything of the old solution is stored there, but it's especially fit in the new case.
So Varun, who's asked the question, is doing something similar in 3D. Varun, you just train the last layer?
So I have like a DeepNet kind of thing. So I train like one layer in the branch and one in the trunk, but it's only like one layer in each that I train, not the entire network.
Yeah, I have to admit, I haven't checked which is the best case, so that could have been done. But here my gut feeling said me, because the neural network is not that big, we could train everything.
Yeah, some of that I see in your plot is like overfitting. Maybe that could be a reason why you're seeing that. It's just because your network
if you
is
go
probably
back,
big.
Jonathan, go back to that plot that you had on the right.
Which one?
Go back a little bit. There was one on the right. This one here to the right. That's the overfitting. That's the overfitting you're talking about. Yeah.
Yeah. And you would think that only training the last layer would overcome this?
Or you start with the last one and then you go upstream. You start with the linear layer and then you go to 1 or 2 upstream. I think, Varun, you did just a linear layer on trunk and branch.
Yeah, just the last linear layer, yes.
Yeah. But because the domain, you changed also the domain. Yeah, you're right. Yeah. I think because we have done another paper on DeepNet with the domain variations, as I said, and the main problem is not just training. The main problem is that you're missing a term. Simple regression would not do it. So you need to account for something that is penalize what is called the conditional shift. Maybe Varun, if you find the paper of some data, you can put it on there. But that's, if you do that, then you actually change a lot. Everybody's doing that. Everybody's doing the same mistake. And sometimes it works. If there's like a parameter, you change a little bit, that transfer learning works. But in your case and Varun's case, you're changing the geometry. And as I said, going from a smooth C infinity geometry to C0 geometry, that creates singularities in the solution. And there's no way you can do that. So you have to penalize what's called the conditional shift. So that's an extra term in the loss function. So the loss function there has other parts, has the regression part that you have, plus this other, you penalize the conditional distribution, the shift in the conditional distribution between the source and the target.
And there's a paper that showed this mathematically, that you have to add this loss?
No, well, mathematically, yes, there is mathematical. There is another paper. No, this paper here that I put shows that that pins in the strong form beat the reaction form.
Yeah.
And actually, I mean, for that, since we have, maybe I can share the. Can I share the screen, Nazanin?
I think I have to stop then sharing.
Yeah, okay, I can share the screen. And let me, can you see my screen?
Yeah.
So this is, I teach my class. This is a paper. Pins, this is not our work. This is from somebody from Stanford. There's a group from Stanford. So they give these bounds and so on, but you can see, for example, this one here. This is the important thing. And I have it, I think I have a table. So this is Ridge method. You can see here. And this is, so look here. It's 2s minus 2. S is the smoothness, right? T is the dimensionality. 2s minus 2 for deep ridge, and 2s minus 4 in it doesn't matter what basis, but basically in the pin. So it's different. See, obviously you want this to be bigger, right? So and again, it's because you're right about the difficulty taking the second derivatives, but I said that's kind of been resolved with JAX. But let's say you somehow you approximate that accurately, then theoretically you can see that I was surprised too, but actually if you think about it, what you are minimizing effectively is a H2 norm in the strong form, right? But you're minimizing the H1 norm of the solution because you have the first derivative of the solution, so it's H1 norm. The strong pins have the second derivative, so it's actually the H2 norm. And that's why you see this extra exponent here, this faster convergence.
Interesting.
Yeah. And also they have examples. These are all their examples from, you can see also even the cost for the heat equation, the Berger's equation, even the cost. You can see here, L2 loss, you see the convergence, L2 loss versus H1 loss versus H2 loss. You see here? Even for convergence, the H2 loss is this one. You are this one. And then L2 is if you don't do any derivatives. It's like that. This is, you can see the convergence here. How it looks. So yes, it is the difficulty. You're right about the, but anyway, there's something. On the other hand, having the variational form helps you with the Neumann, the zero Neumann, I should say. If it's non-zero Neumann, you have to impose it. So,
Thank you. So do we have any other questions for the speaker? I think there is no more questions, but we are waiting for our second speaker. So as he joined us, which I emailed him already, we can move on to the second session.
Thank you, Jonathan.
Thank you for the invitation.
Matthew, are you here? Can you hear me? Matteo.
Can you hear me?
Yes.
Okay.
Hi. Thank you for joining us earlier.
Oh, no problem.
Yeah. Can you share your screen to see if there's any problem?
I can share my
sharing?
screen. Yes. Give me 1 second. So,
Matteo, somehow you look like Mario, who just left our group.
yeah. Where is Mario? He's joining the seminar?
I don't know if he will
I
join
don't think
because
so.
he's driving to his new job.
Yeah. Me and Mario are old friends from Bologna.
Yes, that's why he introduced.
Yeah. Okay, can you see my screen now?
Not yet. Yes, now, yeah.
Now you can, right?
Yeah. Yes. Do you have any video to play?
No video, I just have the slides.
Okay.
Just standard slide.
Okay.
Yeah.
So now I will introduce you. Our second speaker is Matteo Francobaldi. He will be giving a talk on SMLE, safe machine learning by embedded over approximation. Matteo Francobaldi is a PhD candidate in artificial intelligence at the University of Bologna, currently visiting Cornell Tech in New York City. His research focuses on mathematics optimization and machine learning, aiming to improve trustworthiness, safety, and fairness in AI systems. Matteo holds a bachelor's and master's in mathematics and has worked on data-driven techniques for accelerating mixed integer programming and developing hybrid learning and optimization engines. With that short introduction, the floor is yours and you can begin your presentation.
Thanks a lot. So thank you for the nice introduction, of course, and thank you to all of you for inviting me to this prestigious seminar. It's really a pleasure for me to be giving this talk. So as introduced, my name is Matteo Francobaldi. I'm a PhD student from Bologna, and today in this talk, I will describe a method, a framework that we call SMLE, which stands for Safe Machine Learning by Embedded Over Approximation. So SMLE is a framework to enforce the satisfaction of properties in neural networks at training time. Okay, when I say property, I mean in particular safety property, or at least this was the original focus of our project, as the title suggests, even though we are currently, let's say, extending, I am now doing exactly that in New York, trying to extend this framework to support also other kinds of properties. But let me start by introducing the, let's say, motivations of our research. So we all know that today neural networks are really powerful, right? So they can be so powerful to outperform humans in a wide variety of domains. But in the same time, we also know that these systems can be still pretty unreliable, meaning that we are still unable to provide guarantees on the behavior of the system. So we are still unable to guarantee that these systems indeed behave as expected, which is, however, a crucial requirement in those scenarios that can be defined and considered sensitive or safety critical. So scenario where you would like to enforce some requirement, you might need to enforce some requirement. So to give you an example, let's consider a neural network to recognize street signs in a driverless car. So this is clearly a sensitive, critical, safety critical scenario where you might like to enforce some robustness. So actually, this is what I call safe adversarial robustness in the safety community. So here you would like to guarantee that your network is resilient against perturbation in its input. Or maybe we can think of the aviation industry where you might have a system operating as a collision avoidance system. And again, this is a scenario where safety is really a concern, right? So you would like to guarantee some correctness. You would like to guarantee that your network does not take any decision that might lead to a dramatic circumstance, I would say. let's consider the hiring application where you have a neural network that does CV screening, okay? So here your system decides whether a candidate is eligible or not for a job, and here, rather than safety or robustness, you would like to enforce some fairness, for example. So you would like to prevent your network or your system from discriminating let's say a woman in favor of a man, or a black candidate in favor of a white candidate, and so on. So these are 3 cases in which accuracy is essentially not enough, okay? So other than accuracy, you also would like to, let's say, guarantee something more. So beyond accuracy, you need to guarantee the satisfaction of some requirement, okay? But then there is also another case that I would like to show you, and this is a case that, in my opinion, should be considered slightly different from the other 3 cases. This is the case of a rule estimator, okay? So here you have a neural network that estimates the remaining useful life of an operating machine, okay? So this is a common application in predictive maintenance, and this is also a case in which you would like to enforce some property, for example, monotonicity. So why you would like to enforce monotonicity? Well, because you know that the curve that you are trying to estimate is naturally monotonic, okay? So here the idea is that you have some knowledge. Maybe the knowledge that you have is not enough to directly solve the problem, to handcraft, let's say, a solution to the problem, and this is why you want to learn, okay? So this is exactly the reason why you rely on data, but the fact that you don't know enough doesn't necessarily mean that you don't know anything. There might be something that you don't know. Again, you know that that curve is monotonic, okay? And this is not really knowledge that you produced over decades or centuries of research. This is just common sense, right? So you know that the health conditions of a machine with time, over time, can only deteriorate. They can never improve, okay? And so you would like your network to be aware of this fact. But now, why this scenario is different from the other 3? Well, first of all, because here you don't have any concern, right? So here you are not in a safety critical scenario. I mean, if you make a wrong decision, essentially you don't kill anybody, like in the other 2 cases. So if you make a wrong decision, you don't contribute to any social injustice. But this is also conceptually different from the others, because here, rather than enforcing some kind of requirement such as fairness, here you want to enforce some prior knowledge that you have. So here the idea is more the one of teaching your model, the one of informing your system about something, okay? And here, of course, I'm using the word informing because I know that your expertise is mostly in physics-informed machine learning, and so you are certainly more familiar than me with the idea of informing a system. And what I want to say with this, I mean, I want to clarify that our framework can also be used in this direction, okay? But honestly, it's more, let's say, designed specifically for the other cases. So for the cases in which you really have a requirement that you need to satisfy if you want to deploy your system, okay? So just to clarify a bit further, this, let's say, the difference and I would say the nuances and the similarities also between these 2 ideas, so these 2 perspectives. So the perspective of enforcing a requirement into a system versus the perspective of informing a system with some knowledge. So let's try to compare these 2 extreme cases. So I would say that one similarity is the underlying idea, right? So the core idea in both cases is that you want to inject some assumptions into your learning process, okay? So you want to learn from the data, but not only that. You have something coming from outside that you want to incorporate into your learning process. One difference, however, is in the, I would say, in the final high-level goal. So when I inform my system about monotonicity, what I want to do, I want to be consistent with the physical world, okay? So the curve that I want to estimate is monotonic. I would like my network to be monotonic as well. On the other side, I mean, the perspective on the other side is slightly different, because on the other side, rather than be consistent, you want to be compliant with the regulations, okay? So the framework that I am about to present is specifically designed to address these cases. So the case in which you want to deploy your system in a scenario which is highly regulated. And for regulated, I really mean regulated in terms of safety frameworks, okay? So there is a ethical framework, a legal framework forcing some guidelines. And in order to deploy, you need to satisfy these guidelines, okay? So this is more our perspective. Another important difference is that is in the relationship, let's say, between the assumptions and the data, okay? So if I, in the monotonicity case, if I, let's say, observe, if I keep track of the health conditions of my machine over time, what I can expect is that I obtain a curve which is indeed monotonic, okay? So the data from which I want to learn is consistent with the monotonicity assumption that I want to inject. On the other side, this is not really the case. I mean, actually, on the other side, it's more often the case in which these two things, assumptions and data, actually diverge from each other. And here, the fairness example is emblematic in this sense, okay? So here you have your data. You want to learn from your data. Why do you want to learn from your data? Because you want to reproduce and imitate the word that your data describes, but not entirely. This is the crucial point. You like this word, but not entirely. There might be aspects in your data that you don't want to replicate, okay? So for example, again, your data might suggest that a man is on average better than a woman, and this is something from which you want to diverge, okay? So this is the real meaning of doing fairness. So we want to prevent our system to capture the biases and the discriminations hidden in the data. And a last point is in the focus, I would say. So when I teach a monotonic behavior to my system, I do this because I hope to improve its accuracy. So I might expect that a monotonicity aware system on the real data performs better than a monotonicity agnostic system. On the other side, again, this is not always the case. So my fair model very likely will perform worse than my unfair model, okay? And this is because, again, here we have two objectives. We have a property satisfaction and model accuracy. And these two objectives, again, might diverge. And at this point, you have to choose the one to prioritize, or at least from the perspective of this work, we definitely choose one to prioritize, and this is property satisfaction, okay? So first of all, we want to satisfy our property. Then we look at the accuracy. And we already know, you already expect that if you want to achieve property satisfaction, then you have to pay something in terms of model accuracy, okay? So this was just a long introduction, but just to give you the context of my work. So I think we can now dive into the technical details if you want. So again, what do we want to do? We want to train verified by design neural networks, okay? So we are given a neural network f theta. We want to train f theta in order to, so that f theta is good enough in performing a certain task, and then in the same time, satisfy a formal specification of the form P of X implies Q of F of X, okay? Where P and Q are two predicates. So this is what a property is for us, okay? So a property for us is an input-output relationship that somehow describes and characterizes the behavior of our network, okay? So to give you an idea, a visual intuition, let's say, we are given a network and we are given two sets. Why two sets? Well, because the two predicates define a set in the input space and a set in the output space, respectively, right? So we have the set of input satisfying P, the set of output satisfying Q. And now what do you want to do? You want to force a behavior of this type. Okay, so if this happens, so you would say that the property is satisfied, you would say that the network is safe, or you would say that the network is feasible. If it doesn't happen, you would say that the network is violates your property, okay? Now, I have a good news and a bad news. So the good news is that we actually already have an algorithm potentially to achieve our goal. Okay, again, our goal is to train our neural network, which in the same time satisfies a given property. This algorithm is called projected gradient descent, or PGD. So this is a variant of the gradient descent that works more or less like this. So in each iteration, you compute a gradient descent step in the standard way. So you update the parameters of your model, you compute the gradients, you update the parameters in the opposite direction, just the standard gradient descent. But then, before moving to the next iteration, what do? You check whether your neural network with the current parameterization is indeed able to respect the property, okay? And how do you do this? Well, you solve an optimization problem. So essentially, you look for an input X star, which is propagated into an output Y star, such that this Y star maximizes some predefined violation metric delta Q, okay? If you can find such a point, then this is a counterexample. This is a certificate of property violation. And so at this point, you run another optimization process where this time you search over the parameter space of your network. And in particular, you search for another parameterization, which is as close as possible to the actual parameterization, which, however, restores the feasibility of your counterexample. Okay, so you perform a weight projection to essentially bring the point Y star back into the feasible region. So this is the projected gradient descent. So as I said, this is a potential solution to our task, to our goal. The bad news is, however, that this algorithm is intractable, okay? So this is intractable because while the first step is easy to compute, again, this is a standard gradient descent step, it turns out that the verification step is actually very difficult. I mean, it turns out that this problem is actually NP hard. This was proved by Katz in 2017. This was a very important paper for the verification community. But what is the idea? The idea is that the intuition is that if you want to solve this optimization problem, then what you should do, you should somehow formulate your network F by adopting some, let's say, modeling technologies, such as, for example, mixed integer programming or stuff like that. And then you need to optimize over this network. But the problem is that although the verification community is very active and prolific, and it has produced a lot of research to address this problem, although we have a lot of different formulations of a neural network in different modeling languages, so although all these, the truth is, at the end of the day, optimizing over a real-world neural network remains mostly intractable. And this is because real-world neural networks are highly nonlinear, highly non-convex, very large scale. This problem requires exponential time, okay? And of course, the same is for the next step, the projection step, because here you are optimizing over a different space, but the point is still there, the complexity is still there. You still have to handle, let's say, potentially very complex constraints, okay? So long story short, you have an algorithm to achieve your goal. There is no way you can run this algorithm in practical times. So what do we do? Well, this is our contribution. So we propose a particular neural network architecture that we call, again, SMLE, which is specifically designed to facilitate the verification of properties. And we also design a dedicated training algorithm based on PGD, which takes advantage of this particular architecture and which in this way enables effectively the production of verified by design neural networks, okay? So here we are at the core of our presentation, of my presentation. So let's start with the architecture. So we are given a neural network F. What do? We start.
Matteo, can I ask a question?
Sure.
So the constraints that you impose, they are algebraic. Can they be differential?
Differential, yes. This is a neural network, so it's sure differentiable in the parameters.
No, but can you have the derivatives, for example? Can you deal with calculus or let's say Neumann boundary condition or something else, which is described by an ODE or a PDE?
Okay, so you want a derivative?
For example, let me give you an example. A constraint I could have, like, let's say I want a system that is divergence free. The volume doesn't change, right? So I can express that as a divergence of that state is zero.
I think you can do it. This is a normal neural network, so you can differentiate according to its input, with respect to its input. I guess you can do it. Yes.
Yes, it's the differentiable network. Yes. Okay.
Yes. If that was the question.
Well, that was the question, because you're writing as algebraic, but I know in this optimization business, differential constraints are hard as opposed to algebraic constraints.
Yeah. I mean, from my background, I would what we do practically in the implementation, we encode this optimization problem as a mixed integer linear program. So we use binary variables and linear constraints to formulate our neural network, essentially. So that's the idea. And then we run a combinatorial optimization solver to obtain a solution. So that's our approach, actually.
Okay, please proceed.
Okay. Okay, so we were at this point. We have a neural network. So we split the neural network into two components, okay? So a complex component H, which is responsible for embedding, for, let's say, computing an encoding Z into a latent space of an input X. And finally, we have a simpler component G, which simply translates this vector Z into the output space, okay? So essentially, intuitively, what we are doing, we are detaching the last few layers, or even the last layer, which might be linear, for example, from the rest of the neural networks. So you have a very deep and complex component H concatenated with a much simpler component G, okay? Now, at this point, what do? We introduce a trainable and independent over approximation mechanism into the latent space. So essentially, we equip our neural network with two auxiliary models, H lower and H upper, plus a clipping operator. So what happens? The auxiliary models try to predict the bounds of a box bounding Z in the latent space, okay? The clipping operator just makes sure that Z indeed falls into this box. So intuitively, the auxiliary models try to locate, let's say, Z into the latent space. The clipping operator is used as a safety mechanism to make sure that Z indeed falls into this box, okay? So the idea is that at the end of the day, for each input X, we can rely on the fact that the encoding Z lies into a bounding box. It is bounded by a box in this latent space. This is SMLE. Now, how do we use SMLE? So what is the convenience of using this fancy architecture, I would say? So the convenience arises from a verification perspective, okay? So how can we use SMLE to facilitate the verification problem that I showed you before and that in practice is very expensive? Well, the convenience arises from two observations, okay? So the first one is that, as I said, this over-approximation is independent from the main architecture. It is also trainable. So we train it with the main model, but most importantly, it is independent. This means that the user has full control on the complexity of these models, okay? The auxiliary models. And the second observation is that this model can actually be very simple, okay? So they can be simple because they don't need to reconstruct Z perfectly, exactly. This is the role of H, okay? So what they need to do, they only need to roughly locate the region in which Z falls into the latent space, okay? So they don't need expressivity, they don't need learning power. They can actually be simple. Now, if we go back to our algorithm, to our PGD with this in mind, if you remember, we got stuck at this point, okay? So we were unable to efficiently verify our network to efficiently solve this optimization problem. What we can do now is the following. If we substitute the F model with a SMLE version of this model, what we can do at this point, we can forget completely about the complex component H, and we can run this optimization problem over the auxiliary over approximation. So it happens that now in this problem, all the constraints are easy to handle. I mean, G is easy to handle because it's simple by definition. H, lower and upper, are easy to handle because they are simple by construction. And so in this way, we can finally solve our optimization problem. Now, there is no magic in this, of course. So what we are doing, as I said, we are relying on an over-approximation. We are verifying the over-approximation, okay? Not the exact architecture somehow. When you rely on an over-approximation, you lose something. What you lose is exactness. So essentially, if you look at this illustration, what happens intuitively is this. Your network is feasible, but since you are relying on an over-approximation, you might end up with saying that the network is actually infeasible, even though it was feasible. So essentially, the over-approximation trick might produce false positives. It might produce false counterexamples. So we are let's say, renouncing to completeness, we are sacrificing completeness for the sake of tractability. But in this way, we are now able to efficiently solve this step, although inexactly. And the same we can do later in the projection step. So here we can do even more. We can forget not only about H, but we can forget about everything but G. Because here we are given our counterexample, and the only thing that we need to do is restore the feasibility for this. And it turns out that it is enough to manipulate and correct the weights of G in order to restore the feasibility of our counterexample. So our SMLE architecture allows us to, practically execute this algorithm. And this means that we can now achieve our goal.
Mario, one question. Matteo,
yes.
One question.
Yes.
I call you Mario, but Matteo. G and H do not overlap, right? In other words, G is like the last two layers, and then H are all the other layers. So let's say G is there. So they never overlap, because if they overlap, you will overwrite, and you will forget the weights.
Yes, no, they do not
overlap. Yeah.
So G is concatenated with the remaining of the network. G is the last layer. Okay, so all the trick happens before. They are not concatenated. No, so they are not. Okay. They do not overlap. Yes.
Yeah. Great. Yeah.
Okay. Okay, so we said we can partially achieve our goal. So why partially? Because remember at the introduction I said we have two directions here, right? So we have property satisfaction and model accuracy. So in this way we can achieve property satisfaction. The question is now, what about accuracy? Okay, so this question is reasonable. We have different reasons to suspect certain degree of accuracy deterioration. So the first one is the over-approximation mechanism that we are introducing, okay? So the first reason to suspect accuracy deterioration is that the SMLE version of our model F is not equivalent to F itself, okay? We are perturbing the output, and this might represent a source of accuracy deterioration. The second reason is test precision. As I said, we are relying on an over-approximation. We might produce false counterexamples, which means that we might, let's say, force the behavior of the network, even though this was unnecessary. And the third reason, again, what I said before, we might need to deal with a misalignment between the property that we want to enforce and the task that we want to learn, okay? So these two objectives might be in conflict with each other, and if this happens, so there is no way you can achieve both, okay? So if you want to achieve property satisfaction, you need to pay something in terms of accuracy. And now the research question, I would say the main research question of this project is how much do we have to pay, okay? So how much do we have to sacrifice by using SMLE, by using this framework, if we want to guarantee the satisfaction of our property? And this is the question that we are going to investigate in our computational study. So here we adopt 3 benchmarks, okay? So we start with a synthetic benchmark. What does it mean, synthetic? So we design a learning task which is purely synthetic, okay? So we design 9 learning tasks for different input dimensions and for different, let's say, task difficulties, okay? So our learning task, in each case, is a mathematical function of this form. Okay, it's completely synthetic. We randomly generate the data, we enforce linear properties. So our properties are of the form P of X less or equal than P implies Q of F of X less or equal than Q. Okay, so here we have a system of linear inequalities in the input space, a system of linear inequalities in the output space. Here we are pretty much in the scenario of the illustrations, okay? So we have a polyhedron or a polytope in the input and the same in the output. So we start synthetic, we start simple. But then we switch and we move to a more realistic setup. So here what we do is multi-step time series forecasting, okay? So here the problem is that we want to predict the M consecutive values of a time series by observing the N previous values of the same series, okay? And in particular for this, we use data, public data from so real world data from a public repository. And in this case, we enforce this kind of properties. So we, let's say, bound the difference, the divergence between 2 consecutive predictions, okay? So this is not a form of monotonicity. This maybe is more a form of stability, okay? So we want our network to be aware of the fact that if 2 predictions correspond to 2 consecutive time steps, then they cannot be reasonably far from each other, right? They should be reasonably close to each other, okay? So we want a stable network. And in particular, we calibrate this delta max on the data to, let's say, generate different properties. Finally, we consider a classification benchmark. This is another important point that I would like to remark. So our SMLE framework can handle both regression and classification. Here we are in particular considering multi-label classification. Okay, so here the task is I give you a vector of features x1, xn. The network should assign a set of tags, a set of labels selected from the entire set of labels y1, yn, okay? Again, we use real world data from a public repository. Here, what do? We enforce this kind of property. So essentially, we forbid some combinations, okay? Some pairs. So our network assign a set of tags to the input, but it needs to be aware that there are some combinations which are forbidden. So for example, I mean, a real world case for this would be personalized medicine, for example. So suppose that the input is a patient, is the profile of a patient, and you want to assign a combination of drugs that might be efficient for the patient's disease. And so each combination is a therapy, but you know that two drugs cannot be combined together. I mean, there might be pairs of drugs which are incompatible with each other due to, I don't know, drug antagonism, stuff like that. Okay, so this is maybe a form of safety, if you want. So for each task, we have a table of this form. So we prevent the network from combining together forbidden pairs. Okay? Finally, the competitors. So what are the alternative methodologies that we have in order to, let's say, enforce the satisfaction of a property in a neural network? So first of all, we consider what we call pre-process. Okay? So in pre-process, we do this. We enforce the property on the training data. Okay? So if you look at the illustrations, what do? We iterate over the training pairs. And if we find that some pair is infeasible, then we project the output onto the feasible region. So again, here we have to assume inconsistency between the property and the data, okay? And after we know that, so after we have enforced the property in the data, we train our neural network by using any learning mechanism, okay? And in this way, we produce a model which has the advantage of being fast. I mean, here the idea is that the most expensive task, which is our property enforcement, is computed offline. It is computed on the data. Once your data is consistent with the property, you can run, you can do any machine learning analysis and produce a neural network which is fast. But the main drawback is that this network does not provide any guarantee. Okay, this network can violate, and this is because this network is not directly aware of the property to satisfy. Okay, so we enforce the property on the data, but not in the network. Okay, that's the point. So in this illustration, for example, the prediction for Y3 that we call Y tilde3 should be inside the red region, but actually nobody guarantees that it is actually inside the red region. It might fall outside. Okay. So we don't have guarantees. The other competitor that we consider is what we call a post-process. So here we switch, okay? Here we swap these operations. So firstly, we train on the original data, and then we perform output projections, but not in the data, in the predictions, okay? So here, what we do, we predict Y3 tilde, but before delivering the prediction to the user, we check for the feasibility of this prediction. If it is infeasible, we project the prediction onto the feasible region. So we correct the output at inference time. What is the advantage? The advantage is that now we have formal guarantees. This network is consistent, so is feasible with respect to the property, because again, we really, I would say, brutally correct the output of the network at inference time for each inference instance. The drawback is that here we have slow inference, however. So for each instance at inference time, we might need to solve a projection problem. And the projection problem is an optimization problem. This requires time, okay? So this network is not really suitable for those applications like the automotive scenario, where I would say inference time is crucial, okay? So in this scenario, you really don't have time to solve a projection problem at inference time, okay? Finally, we consider an oracle. So an oracle is a theoretical model, which is the model that always makes the most accurate and feasible prediction. Okay, so the oracle is, in the oracle, we essentially project the label, the true data, both at training time and at test time. Okay, so the oracle provides an upper bound on the model accuracy. So the oracle represents the best that we can achieve in terms of accuracy if we want to be feasible with respect to the property. And moreover, Oracle provides us with, I would say, a systematic way to measure the difficulty of satisfying a property. Again, data and properties here are divergent. How do we measure this divergence? Well, Oracle is a good approach, okay? So if Oracle performs very bad on a property and on some data, then it means that this property for this data is very difficult to satisfy. This means that the assumptions and the data are very misaligned, okay? Good.
Sorry, can I have a question?
Yes.
Here for prediction, how did it define the feasible area?
So this is the feasible area, the Q, okay?
Yes,
and
I know. For example, for unseen data, for prediction, this is coming just from training or?
Yes, so this is the test data. So we do not project in post-process, we do not project the test label. We project the prediction because we don't have access to the test label. In pre-process, we project the train label because we have access to the train label. That's the idea.
Yeah, I mean, for example, for test data, how did you, this is for test data, you're defining feasible area. That's my question. Do you have different feasible area for test case? How did you define this? Oh, this is from training?
Yeah, okay, that's an important point. Okay, so the property that you want to satisfy for my method needs to be known at training time. So already at training time, you need to know these two regions. And the idea is that I want to give you a network of theta, which is feasible with respect to these two regions, okay? If you change the property, well, nobody guarantees that for another property, the network is feasible, okay? So you know the property beforehand.
Yeah,
Already
that's true. But for unseen data, for example, for test case, it's hard to say that how we can have this feasible area.
Well, you know the feasible area. And so when you get to the prediction at inference time, it's not that hard to say whether the prediction satisfies the constraints. So here you have linear constraints. So you just need to check that this point satisfies these linear constraints. What is difficult to do is the projection.
Yeah, that's what I'm saying because of this, because for test case, it's not easy to.
Yeah. And this is the main disadvantage of post-process. So here the idea is that you have to find the point in Q, which is as close as possible to the prediction. And yeah, you're right. This requires time.
Yeah, thank you.
Welcome. Okay. The baseline. So here we have the comparison of SMLE of our model against the baseline on the synthetic benchmark, okay? So first observation, as we can see, it's pretty obvious that so here what I'm doing, I am comparing, aggregating the results of our models on different properties. So we considered 6 randomly generated properties for the synthetic benchmark, and I am comparing in terms of R-square, okay? So a value between 0 and 1, the closer to 1, the better it is, okay? So first observation, our models, the performance, the accuracy of our model deteriorates with the difficulty of the property. Again, we have a misalignment, so this is totally expected. Something which is a bit more surprising is that the pre-process, the orange model, as you can see, is above, in most of the cases, so it is above the Oracle one. And this is pretty, at the beginning at least, so this might sound strange because usually you see the Oracle as the most performant model. This is, however, explainable by the fact that, as I remarked before, pre-process is not directly aware of the property to satisfy. So pre-process can violate the property. And this is exactly what's happening here. So Oracle, again, is the best that we can do in terms of accuracy if we want to satisfy our property. So the only way that we have to be above Oracle is by violating. There is no other way. And this is exactly what pre-process is doing here, okay? And we are going to analyze more in details the violation of this model. Another observation is that post-process is very good. Actually, post-process is very close to Oracle. It's very effective, but again, as we remarked also before, it's very inefficient, okay? And it's very inefficient at inference time. And again, in a few slides, we are going to investigate also this. The final observation is that SMLE is quite good, okay? So SMLE is not as good as its competitors, the red model, our model, but it has the main advantage that one, it is feasible, okay? It guarantees the satisfaction of the property, unlike preprocess. And on the other side, it is also efficient. So SMLE doesn't require a projection process at inference time, like post-process, the green one. And this is because SMLE is directly aware of the property to satisfy, okay? So SMLE is property aware. SMLE is verified by design, indeed, okay? Now, if we go to the other benchmark, we can pretty much observe, here we consider 3 properties, we can pretty much observe the same results in the multi-label classification benchmark. So here, maybe the observation is that our models are not that good. All of them, the average accuracy is slightly above 70%, but the important results for us is that SMLE, again, is very close to its competitors. Actually, in some cases, it's even better than its competitors, okay? Which is pretty promising in our opinion. Okay, so here I want to analyze the main drawback of our competitor pre-process. So as I said, the pre-process can violate. Here the question is, how much are we violating, okay? So here I am counting the number of test instances on which the pre-process approach violates, and as you can see, it's significant, okay? So there are properties in which we are close to the 20%, okay? So this approach violates on 2 instances out of 10. This means that this is, I mean, I would not really trust pre-process, okay? So think again of the automotive case or the aviation case, okay? So you have safety concern. You wouldn't deploy such a process, such an approach, okay, in that scenario. And this is instead, for the multi-label classification benchmark, the inference runtime of post-process. So here I am analyzing the runtime of the inference process for our competitor post-process, which is its main drawback. So essentially, how much does post-process requires to produce an output once you give an input at inference time? And in particular, I am reporting post-process against SMLE in seconds. In particular, I'm reporting the relative performance, the relative runtime to pre-process, okay? So pre-process is the fastest the fastest model, okay? So pre-process is fast because it's just a neural net, a standard neural network. SMLE is a bit slower, is around twice slower than pre-process, because in SMLE we are introducing this auxiliary architecture, and we are evidently paying a bit for that. But the point is that the post-process, even though post-process is safe, it requires exponential runtime, okay? So this means that post-process is safe, but again, I wouldn't use post-process on a driverless car, okay? So in a driverless car, you cannot wait this time to process an output, to react to an input, let's say, okay? So this was the last plot. And let's go to the conclusions. So we introduce a framework to enforce the satisfaction of properties at training time in neural networks. So we have achieved good results on synthetic and real-world benchmarks, and in particular in regression and classification, which shows, let's say, the possibility of indeed producing verified by design models only at the price of a slight accuracy deterioration. And finally, we believe that this work supports, if you want, the adoption of artificial intelligence, in particular in those scenarios which are sensitive or safety critical. What about potential follow-ups? So first of all, here in New York, during my visiting period, I am working in particular on specializing my framework on fairness properties. And another follow-up is the idea of using Lagrangian methods. So essentially the idea of using regularizers, okay, to reduce the size of the over-approximation mechanism in order to improve test precision and, as a consequence, model accuracy. So this was the end of my presentation. I hope it was clear enough. And if you have any question, please feel free to ask.
Thank you so much for a great talk. Now we open the floor for questions. Do we have any questions for our speaker?
I had a small question. This is Varun from Brown.
I didn't understand the question, sorry.
Sorry, I was just about to ask my question. So Matteo, how do you define the accuracy for your framework? Because if you have an output which is beyond your requirement, you just scale it inside it. So does that mean that accuracy keeps shifting whenever you project your unwanted output back into the required space? How is the accuracy defined for your model?
So you mean how do we measure how the metrics that we adopt to measure the accuracy? Well, here we have the R-square. So the coefficient of determination. This is a standard regression metric for machine learning systems, okay? Again, it's a value between 0 and 1. The closer to 1, the better it is. For the regression case, in multi-label classification, we compute the accuracy for each single label, and then we average the accuracy. And again, here we have a value between 0 and 1. The closer to 1, the better it is. So for accuracy, I really mean machine learning accuracy, okay? So how accurate my model is on the prediction space. So how accurately can he predict the test data? That's my accuracy.
Yeah, but like say you have a requirement that your model has to predict below 1, and it predicts 1.1, but then you scale it back to 1, right? Based on your framework. Where you project your output back into your requirement space.
Yes.
So does that mean the accuracy is good because you were able to project it back, or does that mean the accuracy of model is like off by like 1.1 minus 1, like 10%?
No, I want to compute the accuracy of the model when it is feasible. So it's the second case. And this is the role of Oracle, okay? That's why we introduced an Oracle. So Oracle represents the best that we can do if we want to be feasible. If we are close to Oracle, we are happy, okay? So that's our accuracy.
It's only for the feasible.
It's only for the feasible, it's exactly. Okay. So here I am comparing on the feasible cases. So I want to be feasible. So there is no reason for me to measure the accuracy on infeasible cases, okay? Because if my network is infeasible, I cannot deploy. That's the point.
Understood. Yep. Thank you.
Welcome.
Do we have any other questions, comments?
Matteo, I have a question.
So go ahead, George.
No, you go ahead first. I asked already, so you go ahead first.
Yeah, okay. Hi, Matteo. This is Panos Dinis from Pacific Northwest National Lab. That's nice work. I'm not sure I understand all the details, but the important thing is what you have as the last thing for follow-up, which is how to decrease the size of the over-approximation, right? Because that's your issue right now. That's why you get the false positives, etc.
Exactly.
Yeah. So I think, I mean, just by listening to you, right? I mean, I don't know if this will make any sense, but I think that what you need during training of these over and under approximators is that you shouldn't just compute things in this latent space Z, right? Because in the latent space, you may be jumbling in information from the input, and it's hard, you have to go to these very crude estimates for Z bar, under and over. So I think that during your training for this H underbar, overbar, and underbar, you should somehow be going back to the input space and check all the time during training what is this extra region that you pick up in addition of capital P. Remember what you were showing in a previous slide, that the region that you had for the predicate for the input is enlarged now, right? This area. I think that during the training, you should be going back and forth between the latent space and the input space to try to make this extra region on the input smaller and somehow to shrink it. So I don't think that you will be able to just shrink it in the latent space without having some information from the input or even from the output space.
Yes, I mean, our idea, so that's a good point. Yes. Yeah. So the test precision depends on the size of this box. Okay.
Yeah. Yeah.
And the larger it is, the more likely we produce false counterexamples, right?
Exactly.
And this produces accuracy deterioration. So our idea is to add a penalty term in the loss, essentially, during our training. So
which will penalize what?
The size of the box. We compute the size of the box somehow. And the larger it is, the more we penalize to keep the over approximation as close as point.
Right. All I'm saying is that I think that in order to get an somehow successful penalization of the box, during training, you should be looking at what is the size of the input and the output extra space that you pick up. So that you see what I'm saying, that because now you're doing it blindly in a sense by only saying that I want to make this size in the latent space smaller, but you don't know how this box in the latent space gets amplified when it goes back into the input space and into the output space, because you have this very complex network H.
Yes, that's good. Yes. So you say that try to measure also the property.
Exactly. So instead of penalizing just the size of the box in the latent space, you should see what is the effect that it has on this extra box in the input and the output space, and try maybe to minimize this during training. By minimizing, I mean the extra space that you pick up in the input, in the output. Yes, so I think that it's like, think of it as a consistency constraint. Now you're trying to impose it on the latent space only. I think if you impose it also during training in the input and the output space, maybe you will be able to reduce a little bit, at least, the false positives.
That's a good suggestion. Thanks a lot. Thanks a lot.
Thank you. But nice work. Yeah.
Thanks a lot.
Yeah.
Thanks a lot.
Thank you.
Thank you. And George, it's your time.
No, I'm fine. I'm fine. It's good talk, Matteo.
Thanks a lot.
I was going to ask about the novelty of with, like, for example, there's structure preserving methods. There are equivariance imposing methods and so on. But I think what you're doing here is you do this decomposition of disjoint network, part of the network, as I said, and then you work in the latent space, and then you introduce also this projection part, which is different from all these other methods, which have sort of the same aim, but right? What's the novelty of your method compared to other methods that are out there? That's what I was trying to.
So first of all, I would say that from the let's say verification perspective, okay. So usually, our background is on verification, okay. So you are given a neural network, you are given a property, you want to verify it, okay. And usually people do this. They do this in post-training phase. You train your network and then you verify. So our idea was, why don't we try to move the effort at training time, so that at the end you have a network which is already verified. Okay, so maybe your training phase and your training algorithm is much more expensive, but then you have a network which doesn't need to be verified. Okay, so that was let's say our intuition. So actually the novelty in general is to propose an in-process mechanism to handle the satisfaction of the property. Okay.
Right. So then you don't do it at the inference time.
Then you don't do it at the inference time. Exactly.
In other words, just as an example, which will apply, for example, in Italy, right? If you pray every day, you don't have to wait for Sunday to pray and save your soul.
Yeah, probably. Yes. Yes. That would be a post process, however.
Yes, that's a post process.
Praying on Sunday. Yeah, you do it a bit every day, and then yeah. Okay.
Thank you. I think, yeah, there is no more question. I cannot see any.
Thank you, Matteo. I have to thank also Mario, who introduced you to us. Thanks for the.
Thanks a lot. Thank you for.
Mario is here. Mario is here somewhere.
Hi. Sorry for the delay. I was driving. I'm in Chicago.
Hi, Mario.
Matteo, thank you so much for the talk. Thank you very much. I hope to see you soon again.
Yes, sure, we will. I am in New York, so we can meet easier than when I was in Italy.
Yeah, exactly. Okay. Bye, Matteo. Thank you very much.
Thanks, Mario. Thanks a lot.
Yeah, ciao,
Thank
ciao.
you, George.
Ciao. Yeah.
Ciao. Bye.
Bye.
Thank you so much for your great talk. And I think it's time to close the session. Thank you, everybody, for joining us today. And I hope everybody has a great weekend ahead. Thank you. Bye.
Thanks a lot. Bye.
Bye.